SpeedCore in steel concrete composite construction. Today is March 17th, 2020. All participants in this webinar are in listen-only mode, but our presentation is interactive. Use that Q&A window to submit questions at any time for our speaker. We will address as many questions have any technical difficulties. We'll do our best to help you through those issues as quickly as possible. There are a few icons at the bottom of your screen, and I want to point out the one that gives access to the resource list. That's the handouts for today's lecture, and those are available for download. You can also find in the register provider with the American Institute. Today's presentation is approved for AIA as well as the learning objectives. It is our intent to fulfill these AIA learning objectives with today's lecture. The resource list also contains information on PDHs. I will go over that process in detail at the end of today's lecture. That today's presentation is being recorded. That does it for today's announcements. Dr. Varma received his bachelor's degree from IIT Bombay, his master's from the University of Oklahoma, and his PhD from Lehigh University. He's been an academic for 20 years. 16 of those years have been at Purdue University. Varma has dedicated his academic and professional life to the development of innovative steel concrete composite structures for the built infrastructure, including commercial, industrial, and safety-related nuclear structures. He has conducted fundamental research leading to the development of design provisions for composite members, connections, and overall structural systems subjected to extreme loading conditions, including seismic, fire, blast, and impact of loading. Dr. Varma serves on many committees, including being the chair of the AISC Task Committee 8 on Fire Design. He is a member of Task Committee 5 on Composite Design, and he's also a member of the AISC Committee on Specifications, as well as ASCE 7 Standard Committee. Dr. Varma has received many awards throughout his career, including the AISC Malik Faculty Fellowship Award, the AISC Special Achievement Award, and the ASCE Shortridge Hardesty Award. Newly added to that list is the 2021 T.R. Higgins Lectureship Award. Today's presentation is the 2021 T.R. Higgins Lecture. Dr. Varma, thank you for being here, and I'll hand things over to you.
I would like to start off by acknowledging the significant contributions of the various project sponsors and the T.R. Higgins Award jury for selecting me for this honor. I would like to convey my deepest gratitude to all my mentors and all my students whom have enriched my professional and personal life. In particular, I would like to express my heartfelt thanks to Mr. Ron Klemenczyk and Professor Bruno. It is a privilege to call them friends and mentors. I also want to thank Dr. Carter, Mr. Kruth, and Dr. Huber of AISC, and Ann Ellis of Charles Pankal Foundation. I want to thank my students, Sohel, Morgan, Ada, and Mubashir, for their contributions to these slides, and also to Tom and Jungle for helping me throughout this journey. This presentation is in 7 modules. These are identified here. They cover everything from introduction to detailing and design for non-seismic, seismic, and fire loading. I will introduce the models as we go. Each module is approximately 10 minutes, and I will wrap up in the end. The first module introduces the system and its use and history. I want to start off with steel concrete composite construction. This is where I started my academic career back in 1996 at Lehigh University. It is truly the best of both worlds, combining the elegance and strength of steel with the rigidity and damping of concrete, combining the speed of steel construction with the fire resistance and stiffness of concrete. Composite columns of various types are now part of the construction folklore. Whether it is concrete-filled hollow sections or concrete encased steel shapes, different shapes and sizes are in use. My first introduction to composite columns came with some prominent examples, like the Columbia Center, 2 Union Square in Seattle, and other innovative designs all around the world. The 2 Union Square in Seattle deserves a special mention because it inspired my PhD research at Lehigh on high-strength concrete-filled tube columns. It uses these mega CFT columns in the lateral system to optimize design. I mentioned this structure in my dissertation as well. Another excellent example of composite construction is the Gateway Tower, or the Seattle Municipal Tower. It uses mega CFT columns at the corners, as shown here. These beautiful structures and others around the world have inspired decades of research and development. We have now got design guidelines and provisions to classify and design different types of composite columns and structures for wind, seismic, and fire loading. Some of our research has contributed to these latest codes and guidelines from AISC. The SpeedCore system has evolved organically from this past with steel concrete composite construction. CPSW/CF, or composite walls, consist of steel modules that are filled with concrete. The steel modules consist of steel plates. tie bars, and maybe shear studs. There are no rebars at all, and no need for formwork or false work for construction. These composite walls can be used as shear walls or elevator core walls in lieu of conventional reinforced concrete walls. The most prominent example of SpeedCore is the beautiful Rainier Square structure in Seattle. Placed next to the Rainier Tower, this building is the newest icon added to the Seattle skyline. Magnuson Klemensic Associates are the structural and civil engineers with some very special partners, architect and client. The contributions, early engagement, and detailed discussions with the steel fabricator and erector were key for the success of this project. The main reason for considering SpeedCore for this project was the speed of construction. The structure was constructed in 10 months, providing savings of about 8 months as compared to conventional reinforced concrete construction. The structure and its conceiver, Ron Klemensic, are so iconic that they both ended up on the cover of the engineering news record. From an engineering perspective, the coupled composite core walls are highlighted within the structural floor plans along the structure height here. They are replacing the conventional reinforced concrete elevator core wall structures. The first application of SpeedCore in a high seismic region is 200 Park Avenue in San Jose. This 19-story structure is under construction and nearing completion right now. This is the webcam view of the structure under construction, showing the initiation of the SpeedCore walls. The SpeedCore walls are serving as the replacement for conventional reinforced concrete elevator core walls. They are highlighted in the structural floor plan on the right. I was fortunate to be a part of the peer review for the design team. SpeedCore walls are remarkably similar to steel plate composite walls used in the design and construction of safety-related nuclear facilities, like the AP1000 plant being constructed in Vogel, Georgia. Extensive research has been conducted over the past 15 years on SC walls, and we were able to leverage all these findings for SpeedCore as well. Particularly the section detailing requirements to prevent local buckling and the shear strength equations are coming directly from this original research on SC walls. Some photographs of the containment internal structures of AP1000, which were all SC walls built in the shop, erected in the field, and then filled with concrete to expedite construction. Lots of fabrication experience and construction lessons learned could be leveraged from these projects as well. Even the containment external building of the AP1000 is made of steel plate composite SC walls, and I was fortunate to conduct the testing, analysis, and support the performance verification of this structure as well. Decades of research and work led to the development of the AISC N690 specification, Appendix N9, of which covers the design of SC walls for nuclear structures. An AISC Design Guide 32, based on this specification, has been available and used even for SpeedCore projects. I was heavily involved with these publications as well. That completes an introduction to the system and its use and history. Since these modules are so technical, and I end up making the presentation remotely due to the pandemic, I wanted to infuse some humor to keep the audience engaged. But all I could come up with were inside jokes. Module 2 of this presentation will focus on section detailing requirements, limits, and strength provisions. Some of these are leveraged from years of research done on nuclear facilities. Now, these are the key components of SpeedCore composite walls. Just a reminder or a reference picture, it's really quite simple. The steel plates or module, tie bars and shear studs, and then the plain concrete infill. For the steel plates, the minimum and maximum reinforcement ratio limits are 1% and 10%. These are based on the range of parameters considered in research. The steel plates have to be connected to each other using ties. These ties can consist of steel bars, rods, or shapes. To prevent local buckling and develop composite action, the steel plates must be anchored to the concrete infill using studs, ties, or a combination of both. Under compressive stresses, as you can imagine, local buckling can occur in the steel plates, in between the anchor points provided by the studs or the ties. The steel plate slenderness ratio is defined as the anchor spacing divided by the plate thickness, S over TP. Years of experimental and numerical investigations conducted around the world are summarized in this plot between the normalized plate slenderness ratio and the normalized local buckling strain epsilon critical over epsilon y. The rectangular shaded region is of interest for design because there is no point in it indicating that when the slenderness ratio is below the limit of 1, the critical buckling strain becomes larger than the yield strain. Using these experimental and numerical results, plate slenderness requirements were developed to ensure compactness, that is, yielding in compression occurs before local buckling. Equations were also developed for slender plates, but the code requires non-slender or compact plates for design. These requirements are a little bit tighter for seismic design, as they very well should be. Now, the design of tie bars is often governed by the design requirements for empty steel modules before concrete placement. Experimental investigations and numerical studies show that the flexibility of empty steel modules is dominated by the effective shear stiffness associated with Virendale truss or frame action. This is useful when considering behavior during transportation, handling, and erection activities. The stability of empty modules during erection, construction, and concrete placement is an important design consideration, which ends up actually governing the tie bar spacing and size and detailing. We looked at the global buckling of a unit width of the empty module, which is conservative but representative. Unit width is defined by the tie bar spacing in the horizontal direction. We found that the critical buckling of empty modules is governed by the same effective shear stiffness, GA effective, which is based on Engesser's equation of shear buckling, not Euler's. This makes the critical load almost independent of the length and end conditions, which is quite remarkable. We were able to confirm this theory and mechanics-based model of empty module buckling using tests conducted previously at Purdue by some of my senior colleagues. You are seeing the buckling of the empty module right here from our laboratory. Using these experimental and analytical results, we developed minimum requirements for the stiffness of empty modules to simplify design checks. The minimum tie size and spacing requirements are summarized here. Alpha is the ratio of the steel plate flexural stiffness to the tie bar flexural stiffness. It governs the value of GA effective and thus the tie spacing to plate thickness ratio. This requirement is to be used along with the local buckling slenderness requirement presented earlier. Together, these two govern the section detailing of composite walls. For instance, an example calculation here shows that for a 24-inch thick wall with half-inch thick steel plates and 1-inch diameter tie bars, it requires a maximum tie spacing of 25 inches for global stability and stiffness of the empty steel modules. But it also requires a maximum stud or tie spacing of 14 inches for local buckling in the composite phase after the concrete has set. Both these requirements have to be met, and therefore different design details are possible. One, only with ties with a spacing of 14 inches and a diameter of 1 inch. Or with tie spacing of 24 inches and corresponding stud spacing of 12 inches to meet both the requirements. Now these are the recommendations for the effective stiffness values when modeling SpeedCore walls for analysis for calculating design demands. The stiffness should account for concrete cracking corresponding to the design scenario. Now the engineer can perform a section moment curvature analysis to estimate stiffness and account for the extent of concrete cracking, which can be quite limited if drift governs the design for lateral wind loading. In the absence of better information, we have provided some simple stiffness recommendations for the engineer to consider or use in their design. The in-plane flexural strength of steel plate composite walls can be calculated using the plastic stress distribution over the composite cross-section. It's quite simple, with the steel limited to yield stress Fy in both compression and tension, and the concrete limited to 0.85 F prime C in compression. Equations have been developed for calculating the plastic moment capacity. These equations are provided in a design guide, which I will mention at the end of my talk. The in-plane shear strength is governed by composite action between the steel plates and the concrete infill. Now the concrete behavior is orthotropic, with cracking in the tension diagonal direction and compressive stress field forming in the other orthogonal diagonal direction. The trilinear behavior of the composite wall in shear is shown here, with stiffness before and after concrete cracking. Eventually, the in-plane shear strength is governed by von Mises yielding of the steel plates, while the concrete compressive stress is limited to values less than 0.7 F prime C. Equations for estimating the stiffness before cracking, after cracking, and the in-plane shear strength corresponding to the von Mises yield strength are all provided. This in-plane shear behavior theory has been validated experimentally by conducting large-scale tests in the US and also abroad. You can see the trilinear shear force strain curves compared with experimental results shown on the right-hand side here. The principal directions measured by the strain gauges and the diagonal tension cracking in the concrete leading to orthotropic concrete behavior are also highlighted. The steel plates were removed in order to observe and mark the concrete cracks after testing. This slide shows the extensive experimental validation of the in-plane shear strength equations using test results from around the world. These in-plane shear strength equations are given in the AISC specification as well. They're conservative and can be used with confidence. Since I was putting together this presentation, I wondered why the chicken crossed the road. It seems that the chicken behind it was not social distancing properly. Just a little bit of humor to address the dryness of the technical presentation. The third module focuses on the in-plane behavior of flexure-critical SpeedCore walls, their stiffness, strength, and deformation capacity in particular. The experimental results that I am about to show are applicable to both seismic and non-seismic behavior and to coupled or uncoupled SpeedCore walls. The parameters considered in the experimental investigations were the axial load level, plate slenderness ratio, tie bar size and spacing, and the use of shear connectors along with tie bars. This module will summarize the test matrix, setup, the loading protocol, and the observed experimental behavior along with detailed findings. The specimens were approximately 1/3 scale models of composite walls. Their thickness was 9 inches. The steel plate thickness was 3/16 of an inch. The wall length was 36 inches and the height to length ratio was 3. Definitely a flexure critical wall. The axial load level varied from 10% to about 30% of AGF prime C. The plate slenderness ratio limit was 26, so there were specimens within the limit and just outside the limit as well. 2 tie bar spacings equal to wall thickness and wall thickness divided by 2 were considered. Here are some of the structural drawings of the specimens along with the test matrix and the parameters identified. 3 of the 5 specimens were identical, with the only difference being the axial load level. The 4th specimen had higher plate slenderness ratio and tie bar spacing. The last specimen introduced shear studs in between the tie bars to reduce the plate slenderness value, again back to within the limit. The tie bars were fillet welded from the outside, which worked quite well in the specimens and also in the actual structure. A special welded detail was used to connect the 3/16 steel plates to the base plate. The 3/16 plates were fully welded to a 3/4 transfer bar in the shop. The 3/4 transfer bars were CJP welded to the base plate in the field. Now this is only needed for the test specimens because the steel plates were scaled and therefore thinner. This is a schematic of the test setup with the specimen, the fixed base, the axial loading arrangement, which is free to rotate about the base, and the lateral loading applied using hydraulic actuators. This is showing a photograph of the same setup with the details highlighted. Testing went quite well with great effort from the students and the technicians. This is showing photographs of empty steel modules of specimens in the laboratory. You can see the different internal details and configurations. Self-consolidating concrete with a nominal compressive strength of 6,000 psi was used to fill the modules. The APC-24 cyclic loading protocol was used with 6 elastic cycles used to establish yield displacement values, delta Y, and several inelastic cycles at different multiples of delta Y. The expected flexural strength, calculated using the plastic stress distribution method for composite columns, was used. Accounting for the effects of axial force and PM interaction, the flexural capacities for the specimens were estimated using this method. Now, this is the cyclic lateral load displacement behavior of the specimen subjected to 10% axial load and with the tie spacing equal to wall thickness divided by 2. On the top, the x-axis is in terms of delta y or multiples of delta y. The occurrence of various events A through E are highlighted on the load displacement response. Event A corresponds to yielding, which occurs before event B, which is local buckling of the flanges. Event C corresponds to local buckling of the webs. D corresponds to initiation of fracture, and E corresponds to total fracture. As shown here, local buckling occurs after yielding but before the peak load. Fracture reduces the load capacity and eventually causes failure. The lines corresponding to the plastic moment capacity and 80% of the maximum load are also indicated here for comparison. This slide shows photographs of the specimen during yielding and local buckling initiation in the flange, which was point B during the 2 delta Y cycles. Extensive local buckling occurred during the 3 delta Y cycles, which was point C, corresponding to the occurrence of web local buckling as well. Extensive local buckling and fracture, point D, is shown here during the 4 delta Y cycles. Complete fracture, point E, and concrete debris oozing out during the 6 delta Y cycles are shown here. This slide shows the base moment versus plastic hinge rotation responses for a couple of those wall specimens with axial loading of 10% and 20%. The x-axis is the rotation in radians. We can use these moment versus rotation plots in a couple of ways. First, we derive the moment versus curvature responses of the plastic hinge and marked various events on it. On the right is a comparison of the experimental moment curvature envelopes with a cross-section fiber analysis, showing excellent correlation between the fiber analysis of the cross-section and the measured moment curvature responses. The fiber-based moment curvature response was then used to evaluate the steel and concrete strains at various events along the moment curvature response. Peak load was reached consistently when the steel reaches 2 times the yield strain in compression, or a strain of about 0.004. The behavior in the elastic cycles was used to assess different flexural stiffness values: the gross uncracked stiffness, the cracked EI effective for moment curvature analysis, and the AISC EI effective equations. The initial stiffness compares well with the gross uncracked stiffness. The secant stiffness compares well with the cracked EI effective values, both from the moment curvature analysis and also with the AISC EI effective equations. The plastic rotation capacity of the hinges at the base of the wall specimens were determined and assessed. All specimens have plastic rotation capacity between 0.014 and 0.02 radians, which is quite good. The rotation capacity decreases slightly with axial load level and also with the larger tie spacing. In summary, the plastic stress distribution method and fiber analysis method can be used to estimate the flexural capacity and the flexural stiffness of wall specimens. The behavior is consistent with that of composite columns. Plastic rotation capacities were in the range of about 0.015 to 0.02 radians, which is very good. Weak moment corresponds to steel compressive strain of 2 times the yield strain. And the fiber models are quite effective in modeling behavior. This brings us to the end of the third module, focusing on the experimental behavior of flexure critical walls. Which brings me to an interesting question. What do you call Chewbacca when he has chocolate stuck in his hair? Apparently the answer is a chocolate chip Wookiee. This brings us to the fourth module, which builds upon the experimental research and develops nonlinear analysis and modeling recommendations. 3 models with different levels of complexity were developed and for different purposes. 3D FEM models, 2D FEM models, and then OpenSea's fiber-based models. All of these models are connected and calibrated to each other, including experimental results through the use of effective stress-strain relationships for the steel and concrete. The 3D finite element models were sort of a kitchen sink approach, modeling the entire test setup and all the nuances and details of the specimens, including plates, ties, studs, and their interaction between the steel and the concrete, etc. 3D constitutive models of steel and concrete material plasticity, damage, and fracture were used to model the behavior in detail. The shear force slip behavior between the ties and the shear studs were also modeled. Concrete compression plasticity, confinement, and tension cracking were explicitly modeled in the 3D FEM models. The 3D FEM results from the monotonic analyses compared very well with the pre-peak envelopes of the test results. Events such as steel yielding, local buckling, and peak strength compared very well. However, monotonic analysis did not capture the post-peak behavior because it did not include fracture or did not reach fracture in these monotonic analyses. Multiple cycles of histolytic behavior are needed for that. The results of cyclic analysis compare very well with the envelopes of the test results, as shown here. But the histolytic behaviors in quadrants 2 and 4 were not represented due to the inherent limitations of the concrete material model cyclic behavior that we were using in our program Abacus. In summary, the cyclic analyses conducted using the 3D FEM models could simulate the behavior, particularly the envelopes of the responses, including the fracture failure of the steel. However, the 3D finite element models are quite complex and time-consuming. They are good for evaluating local specimen behavior and failure. However, for system-level analysis, we need simpler 2D finite element models made from layered composite shell elements or 2D fiber element models. Both of these, however, cannot model some aspects of behavior directly. So we developed effective stress-strain curves to indirectly incorporate yielding, local buckling, confinement, etc. conservatively. We developed these effective stress-strain curves using the results of the 3D finite element analysis by post-processing the results from monotonic analysis and averaging them over the plastic hinges. For example, the effective stress-strain curve of steel plates undergoing local buckling were derived. Similarly, for the concrete infill, we were able to account for the effects of transverse interaction and confinement by post-processing results from the 3D monotonic finite element analysis. The effective stress strain curves for the concrete in compression, which was confined, were also derived. These are the simplified, generalized, and conservative effective stress strain curves that we recommend for the steel and concrete fibers to indirectly and implicitly account for yielding, local buckling, transverse interaction, confinement of the concrete, and eventually failure as well. We implemented these effective stress strain curves in a simple 2D finite element model using layered composite shell elements for the composite walls and truss elements for any of the flange or closure plates. And the results were quite comparable to the much more complex 3D finite element models. Whether you look at monotonic behavior or you look at cyclic behavior, the 2D FEM models run orders of magnitude faster and give approximately the same or comparable results with the 3D finite element models. Therefore, we use these 2D models extensively for system-level seismic analysis. Similarly, we use these effective stress strain curves along with the 2D fiber-based element in open seas. And the results compared even better with the test results because these models can better account for the cyclic behavior of concrete with pinching in quadrants 2 and 4 of the cyclic behavior. The next module focuses on the seismic behavior and capacity design principle for the SpeedCore systems. Now, seismic design can be performed according to ASCE 7 standards and the AISC 341 seismic provisions. Performance-based design can also be conducted, but it is a little bit beyond the scope here. However, the numerical models needed for performance-based design are similar to those I just presented in Module 4. In seismic design, the concept of response reduction factor R, the overstrength factor omega naught, and the displacement amplification factor CD are well known. Depending on the ductility of the structure, we take higher values of R to reduce the earthquake force demands and calculate the inelastic drift by multiplying the elastic drift by a CD factor. ASCE 7 provides these factors. For the uncoupled SpeedCore system, the R value was already listed at 6.5. For the coupled SpeedCore system, ASCE 7 does not provide an R value. The highest value for R for any system in ASCE 7 is equal to 8. Now, FEMA P695 is a systematic procedure to assess the seismic collapse margin of structures designed using a set of design criteria and seismic factors R, omega naught, and CD. The process includes many steps, the first of which is having a consistent design method, using it to design several groups of archetype structures, developing nonlinear models able to model the failure modes of the structure, and subjecting them to scaled suite of ground motions. These ground motions are scaled to conduct incremental dynamic analyses, and finally, statistical evaluation of the results is performed and the collapse margin is assessed. That is the FEMA P695 procedure. It is important to note that there are two types of SpeedCore systems, coupled and uncoupled. Both are viable and acceptable. In fact, in the same building structure, SpeedCore can be coupled in one direction and uncoupled in the other. Uncoupled uncoupled SpeedCore walls of different cross sections are possible, with planar walls and C-shaped walls being common. Walls with semicircular or circular boundary elements are also possible. For the uncoupled SpeedCore system, seismic design provisions were already provided in AISC 341, 2016, but enhancements have been added in the upcoming 2022 revisions. The uncoupled walls are required to be flexure critical, with height to length ratio greater than or equal to 3. And walls are required to have boundary elements or flange plates. These are the enhancements added in 2022. A comprehensive FEMA P695 study was performed on the uncoupled SpeedCore walls, and the R factor of 6.5 given in ASCE 7 was verified. The study included several archetype structures, including 3 to 12-story structures with planar walls, 15 to 22-story structures with C-shaped walls. Nonlinear models, dynamic analysis, and the whole 9 yards were conducted for the 22 sets of FEMA ground motions that were scaled. Statistical analysis of the incremental dynamic analysis showed that all the archetype structures with uncoupled SpeedCore walls designed according to the AISC seismic provisions passed the adjusted collapse margin ratios set forth by FEMA P695. Even though collapse was defined quite conservatively with 3% drift ratio, where the SpeedCore walls had not yet failed. Now, this portion is not the focus of this presentation, but the report on the FEMA P695 studies of the uncoupled SpeedCore walls is available in AISC, and the link is mentioned in the end. For the coupled SpeedCore system, we decided to target the R factor of 8, which is the highest possible in ASCE 7. Additional system-level ductility beyond that of the uncoupled system can be achieved by spreading the inelastic behavior and yielding along the height of the structure. This was a great opportunity to develop a capacity-based design method to achieve excellent seismic behavior. There are really two potential sources of inelastic deformations in the coupled SpeedCore system: flexural plastic hinges at the ends of the coupling beams and flexural yielding at the base of the walls. The preferred mechanism is to form hinges in most of the coupling beams along the height of the structure before the last hinges form at the base of the walls. Basically, a strong wall, weak coupling beam design approach. Coupling beams spread plasticity along the height and eventually fracture, while the composite walls continue to provide inelastic behavior. For seismic design, the coupling beams will also be composite concrete-filled steel box section, which is a shout out back to module 1 of this presentation when we talked about concrete-filled composite sections. Now this slide shows the target nonlinear pushover behavior. The composite coupling beams are designed for the reduced earthquake force with an R factor of 8 at point A. But the walls are designed at point B, which corresponds to greater demands associated with the plastification of all coupling beams along the structure height. Point C is where you develop hinges at the base of the walls as well, and eventually fracture at point D. This is the capacity design principle for the coupled SpeedCore system. several archetype structures, including 3 to 12-story structures with planar coupled walls, and 18 to 22-story structures with C-shaped coupled walls were designed using the capacity design method. All the coupling beams were also composite, namely concrete-filled steel box sections, which we saw earlier in Module 1. Now this slide shows the system-level pushover behavior obtained using OpenC's fiber-based models for 8-story and 18-story structures. The events A through D indicate that the behavior follows the capacity design principle. Coupling beams yield at point A, which is close to the earthquake design force. The beams undergo yielding along the structure height between points A and B. The wall yields, or the wall forms plastic hinges at point C, and fracture of the coupling beams occurs at point D. This is showing the same system level behavior, but now using the 2D finite element model. In these figures, black indicates behavior beyond yielding. Again, the system shows the designed and the desired behavior. Between A and B, all the coupling beams along the height of the structure undergo yielding. At point C, plastic hinges form at the base of the walls, and the coupling beams reach strain levels corresponding to fracture at point D. Let's confirm this behavior for earthquake-induced cyclic loading by nonlinear time history analysis. Let's take the ground motion record and scale it according to FEMA P695 to be the design basis earthquake for the same 8-story structure. Only a few events, for example, initiation of coupling beam yielding and initiation of yielding in the walls, occurs in this response. There is some spread of yielding along the height and some initiation of yielding at the base of the walls, as seen here in these post-processed pictures. When scaled further to the maximum considered earthquake level, all the coupling beams yield along the height of the structure, and the wall also undergoes yielding at the base, which is seen in the responses and the post-processing of the results. For the failure level earthquake with a scale factor of 7, corresponding to a 5% story drift, all events occur in a similar order. The coupling beams undergo yielding, the walls undergo yielding, there is propagation of yielding all along the height of the structure in the coupling beams. There is initiation of fracture in the coupling beams, and then total fracture of the coupling beams at the end of the record. The walls do not collapse. Just some large permanent deformations occur at the end of the record. Let's watch a video of the seismic behavior simulation for the failure level earthquake. This video shows the time history response of the structure subjected to the scaled earthquake level, causing a drift ratio of about 5%. The ground motion is on the top, and the cyclic roof displacement response is shown on the bottom. The contoured plots show extensive yielding in the coupling beams along the height of the structure and at the base of the walls. The black color in the contour plots indicate fracture at the ends of the coupling beams and the initiation of fracture at the base of the walls. This is the response for the failure level earthquake that corresponds to an interstory drift of about 5%. At the end of the record, there is some permanent deformations, but there is no collapse or failure of the system. This module summarized the seismic behavior and the capacity design principle. Let's take a look at a short module on the seismic performance requirements for the coupled SpeedCore system. Now, the seismic design criteria for the coupled SpeedCore systems will be a part of the new AISC seismic design provisions, the NEHRP 2020 provisions, which are already published, and also mentioned in the ASCE 7 standard. FEMA P695 studies were conducted to verify the seismic response factors of R, omega naught, and CD. It was once again the whole 9 yards, including several archetype structures and groups, including 3 to 12 story structures with planar coupled walls, and 18 to 22 story structures with C-shaped coupled walls. Nonlinear models were developed and analyzed for 22 sets of scaled ground motions by 2 independent teams, one at Purdue University and the other at the University at Buffalo. A conservative failure criterion of 5% drift ratio was used, as the structure did not fail or collapse. Thousands of incremental dynamic analyses were conducted and the results evaluated statistically. The collapse margin ratios met the FEMA P695 criterion with good margin, and all the seismic design factors were verified. Consequently, the R, omega naught, and CD values were verified and accepted into the ASCE 7 standard in the upcoming edition of 2022. The upcoming AISC seismic design provisions in section H8 for coupled SpeedCore system are based on the FEMA P695 studies and the capacity design principle. Some additional requirements are placed on the coupled SpeedCore system. The wall height to length ratio is limited to 4. The coupling beams are required to be concrete-filled composite sections with flexure-critical behavior and length-to-depth ratios between 3 and 5. All of these limitations were based on the archetypes included in the FEMA P695 studies and the desired ductility. There are slenderness or compactness requirements for the composite coupling beams and the composite walls. Coupling beam to wall connections have specific performance requirements. They should develop the flexure and shear strength of the coupling beam, and they should have a rotation capacity of 0.03 radians before the strength degrades to 80% of the plastic moment capacity of the coupling beam. A schematic of the required coupling beam moment versus chord rotation envelope is shown on the left. Now, all the connection models assumed in the FEMA P695 studies were consistent with this required performance as shown on the right-hand side. In summary, we need coupling beam to wall connections that can meet these performance requirements for strength and deformation capacity. Some were tested in the past, and additional testing has recently been completed. The coupling beam elements, which include the flanges, the webs, and the concrete infill, have to be connected to the composite wall to transfer all the stresses and forces. Various connection types have been considered, vetted by the industry and fabricators, and 3 final candidates were selected. 2 coupling beam length to depth ratio extremes are being considered of 3 and 5. Thus, 6 connection tests have been conducted recently. 2 of these connection types are shown schematically here. On the left is a connection type 1B, where the coupling beam flange plates penetrate into the walls and the coupling beam web plates are lapped and welded from the outside to the composite walls. Another connection type 3, shown on the right, has continuous web plates between the composite wall and the coupling beam, whereas the coupling beam flanges penetrate into the walls and are welded. The actual test specimens are about 1/2 scale, and the coupling beam to wall connections are tested as shown here. The wall is post-tensioned to the strong floor, and half of the coupling beam height is subjected to cyclic lateral loading according to ATC 24 guidelines to failure using actuators. An actual photograph of the test setup in the lab with all the parts identified is shown here. The connection region was whitewashed and highlighted as shown here. This is connection type 1B with the coupling beam length to depth ratio of 5. This is the lateral force displacement behavior of the specimen subjected to the ATC 24 loading protocol. You're seeing the lateral force versus beam end displacement response. The backbone curve has been identified, and 80% of MP horizontal lines have also been shown. This is showing the complete response along with the occurrence of various events A through E. So the same result where A corresponds to yielding of the flange, B corresponds to initiation of fracture, C corresponds to initiation of local buckling of the flanges, local buckling of the webs, and then eventually total fracture of the flange as well. Horizontal lines corresponding to 0.8 MP are indicated in blue, and vertical lines corresponding to a rotation capacity of 0.03 radians are also identified here. This slide shows the envelopes of the beam end moment versus chord rotation response for connection 1B, showing a rotation capacity that is in excess of 0.035 radians as shown here. Photographs of the specimens during the 3 and 4 delta Y cycles at chord rotation of about 0.035 radians is shown here. Shows extensive local buckling of the coupling beam flanges and of the webs, and also the fracture initiating in the flanges as well. Let's watch a time-lapse video of the connection performance, particularly in the combined 1 to 5 delta Y cycles. Since the connection region is whitewashed, you will be able to see the yielding of the steel plates, followed by local buckling of the flanges, and then the webs. Eventually, the fracture of the connection through the flange plates and the webs will be evident. Beginning to see the initiation of fracture, the local buckling of the flanges, and the webs. You're seeing that, and then the propagation of fracture through the connection. In summary, coupling beam to wall connections have been tested and validated for SpeedCore. Additional testing is underway, and so far 2 connection types have been completely verified for the SpeedCore application with different length to depth ratios of 3 and 5 to show acceptable performance. This brings us to one of the last and perhaps most important module, which focuses on fire resistance and design. The focus is on fire resistance of unprotected composite walls. We have looked at thermal and structural behavior to uniform and non-uniform heating, both experimentally and numerically. I will talk about the numerical models that were developed, benchmarked using test results, and then used to conduct parametric studies. All the results were used to develop equations for calculating strength as a function of temperature and the fire resistance rating in hours. I will end with a brief discussion of vent hole design and its need for composite walls. There have been a few fire tests around the world on composite walls. This photograph shows some furnace tests that were conducted in China. The composite wall was subjected to gravity loading and the standard fire temperature time curve. Some of the experimentally observed failure modes included local buckling of the steel plates, weld splitting at the corners, and global instability. We conducted our experimental investigations on the same wall specimens we had used earlier in Module 3 of this presentation for cyclic testing. Since the failure in those tests was localized at the base, we were able to reuse the remaining length of the specimen for fire testing. Specimens were 9-inch thick with 3/16-inch thick steel plates, slenderness ratios of 24 and 48. Both uniform and non-uniform heating were included. The actual load levels in the tests were about 20 to 30% of the wall concrete strength. We used a self-reacting structural test setup, similar to the column setup used in the past. The ends of the wall specimens were cast in reinforced concrete blocks at the ends. Axial loading was applied using a hydraulic ram, and cylindrical bearings were used at the ends to achieve pin end conditions. Thermal loading was applied using ceramic fiber radiant heaters that surround the specimen completely. These heaters can be controlled to apply different surface temperature time curves. In these tests, they were used to apply the effects of standard fire temperature time curves directly to the specimen surfaces. This is showing a photograph of the specimen with the structural setup and the heaters all around it. Thermocouples and other sensors for measuring thermal and structural behavior can be seen. This is a photograph showing the heaters in operation. You can see the red heat through the safety shield. You can also see some concrete, some cracking and moisture coming from the end reinforced concrete blocks. Let's look at some typical experimental results with the measured surface temperature time curves shown on the left. Surface temperatures exceeding 1000 degrees centigrade can be seen. The thermal gradient through the 9-inch thick wall is shown on the right. There was a large nonlinear thermal gradient that stays through the cross-section even after several hours of heating. The central concrete core temperatures are quite low. Let's look at some more results. This slide shows the axial displacement versus time, and also with respect to the surface temperature for all the specimens subjected to uniform heating. There were really no significant events, failure, or loss of axial load capacity. The behavior was stable for axial load levels up to 30% and heating up to 3 hours, even for the 9-inch thick small scale specimens. Photographs of the specimens after heating showed some local buckling of steel plates in the heating regions. The local buckling occurred in between rows of shear studs or ties as expected. Most fire photographs show local buckling between the studs or the tie bars. The wavelength and amplitude of local buckling changes with the tie spacing. Although there was no failure, the steel plates were removed in order to inspect damaged and cracked. Significant. This test was also conducted using the same setup. The summary side reaches a temperature of about degrees centigrade in about 2 hours. Degrees centigrade. The tie bars don't act as thermal bridges failure either. In summary, even the small scale 9-inch thick specimen had more than 2 hours of steam vent holes needs to be considered, which we will talk about soon. When non-uniform heating is applied, there is some out-of-plane bending, but no failure. 3D finite element models of all the tested specimens were developed. All the components were modeled explicitly similar to previous models, but this time along with thermal and mechanical properties to simulate behavior under fire loading. Now, connecting the thread all the way back to module 2 of this presentation, since composite walls have a lot of possible cross-section shapes and geometries, we idealize composite wall for analysis. Unit width is defined by the tie spacing we summed up along the wall perimeter to conservatively estimate the wall strength. We developed refined 3D finite element models of the unit width columns to investigate and evaluate behavior. We modeled the steel plates, ties, shear studs, and the concrete explicitly. The models were benchmarked using experimental results from other researchers and also from our test program. Both thermal and structural responses, like the actual displacement versus time, were benchmarked. The experimental results were compared with those from the 3D finite element models and also from the unit width columns. Both models could be verified using the experimental results. Excellent comparisons between the experimental behavior and the 3D finite element models were observed. For example, here we can see the local buckling between the tie bars for the specimens and the finite element models. We also developed a simpler fiber-based column inelastic buckling analysis program that can account for the effects of fire loading on thermal and structural behavior. It conducts a nonlinear heat transfer analysis to calculate the thermal gradient curvature temperature analysis for the thermal gradient, followed by column inelastic buckling analysis using these results. Thus, the program does thermal and structural analysis for composite walls and columns. This is a standalone independent program that you can download from the Purdue repository mentioned here. This simpler model was benchmarked using the detailed 3D finite element models and the experimental results. The program is capable of taking in different fire scenarios, thermal properties and insulation, and different material models also. Results can be post-processed to understand behavior. For example, thermal gradients through the composite cross-section and the actual displacement versus time response of the composite member is shown here along with the events identified from post-processing the results. The program was used to conduct extensive analytical parametric studies on unprotected SpeedCore walls. Various wall geometries and dimensions, steel and concrete material properties, and loading ratios were considered. I won't get into the details of all the results, but summarize them here. Results indicate that the time to failure depends on the wall thickness, the wall height to thickness or slenderness ratio, the load ratio, and also on the end conditions. Generally, walls with story height to thickness ratio greater than 10 reach their strength due to global buckling. The fire resistance of unprotected composite walls is quite significant, particularly because the concrete infill takes very long to heat up in the thicker walls. Now, non-uniform or one-sided heating results in thermal bowing and second-order movements in the walls. Only for walls with story height to thickness ratio greater than 20 and subjected to one-sided heating, insulation or fire protection is needed on the exposed surface. This is generally not the case because typical wall height to thickness ratios are less than 10. Typical SpeedCore wall designs do not need any fire protection or insulation. The results from these experimental and numerical investigations and parametric studies were used to justify the need or the lack of need for fire protection for the composite SpeedCore walls used in the 200-part structure that I talked about in Module 2. We were able to compile all the analytical results, parametric studies, and experimental results to develop an equation for calculating the axial strength of walls as a function of the steel surface temperature. This equation accounts for the ambient strength PNO, the wall thickness and the slenderness ratio of the wall through the PE term here. This equation is included in the upcoming AISC specification Appendix 4. We were also able to use all this research to develop a fire resistance rating equation for composite walls and columns. This equation calculates the fire resistance rating in hours and depends upon the utility ratio at ambient, the wall thickness TW, and the wall story height to slenderness ratio, to thickness slenderness ratio, H over TW. It correlates quite conservatively with the analysis and test results. This equation is also included in the upcoming AISC specification in Appendix 4. Typical SpeedCore walls have considerable fire resistance rating values. For example, a SpeedCore wall with thickness of 24 inches, axial load ratio of 10%, and wall story height to thickness ratio of 10 has a fire resistance in excess of 4 hours by a significant margin. Now I want to draw your attention to an important topic. Since this is a concrete filled steel structure, steam from the concrete moisture content can get trapped and develop pressure within the walls. This pressure can be vented by design and detailing vent holes which are now required by the AISC specification. This video was for the non-uniform heating specimen where one side was not exposed. While the steam venting phenomenon occurs for all faces, it is seen most clearly from the test here. You can see the steam puffing from the vent holes. The design of vent holes is based on the concept of pressure relief valves in boilers. I am a boilermaker after all. We calculate the vapor or steam generation rate using the moisture content of concrete and the calculated thermal gradients. We can select an allowable buildup pressure in the steel vessel and design the vent hole area and spacing. The equation is a bit involved to show here, but in most cases, we found that 12-foot spacing in both directions and 1-inch diameter holes are sufficient to reduce the steam pressure down to allowable values. It is simple, but important and quite relieving to the engineer as well. This vent hole requirement is included in the upcoming AISC specification Appendix 4. Now we have arrived at the end of our long story, but the development and work continues. The research project is now focusing on the use of bolted splices and connections for non-seismic design of SpeedCore walls. This is very promising to improve construction speed and reduce the use of welding, particularly in non-seismic applications. We are looking at a variety of coupling beam to wall connections and wall to foundation connections for both seismic and non-seismic conditions. We have also been working on a research project focusing on the performance-based fire design of connections between the composite floor system and the SpeedCore walls. This includes testing and analysis. We are just about to begin testing for this project. I want to mention some publications. All the research and development discussed in this presentation has led to the inclusion of SpeedCore in the upcoming 2022 AISC specification, seismic provisions, and the ACE 7 standard. Provisions, the seismic design provisions are also already published as part of NEHRP 2020. In order to help practitioners and users, we have also co-authored a Design Guide 37 that is based on the research and development in these codes. It is meant for design for wind, seismic, and fire loading. Design Guide 37 is complete and coming out shortly. It can be used for the design of both coupled and uncoupled SpeedCore systems. It's a comprehensive design guide full of design examples for both wind and seismic, design of coupled and uncoupled SpeedCore systems, and also for fire design. All the MathCAD design examples that are presented in this design guide are also available to download from the Purdue repository. For fire-resistant design, since my presentation was brief, I want to mention some available resources. You can access presentation videos from my YouTube channel and also from AISC and the Charles Pankow Foundation. Our computer program for fire design and other fun things can be downloaded from this Purdue repository link. You can download, install, and use them on your computer. AISC maintains a full website for SpeedCore where you can find all our reports, links, publications, and a wealth of information. Just search for AISC plus SpeedCore. These are the links to some of the reports that I mentioned during my presentation that you can also get from the AISC research library as well. With this, I would like to open up the floor for some questions and discussion. Thank you.
All right. Thank you very much, Dr. Varma. We've got a lot of questions from the audience, a lot of interest in today's presentation, so thank you very much. We do have some polling questions as well for the audience, but let's get to a couple of questions right away, and then we'll jump over to the poll questions. So, Amit, our first question is this type of shear wall still suitable for high-rise buildings where wind loads are governing?
Thank you, Brent, and thank you for the question. This type of a structure is very well suited for high-rise building where wind governs the design. In fact, it is under development for a few projects where they are located in non-seismic regions and wind is essentially the governing load combination. Even for the Rainier Tower project, Rainier Square project, wind was an important design consideration.
Okay, thank you. Our next question was asking about the tie bar. What is the role of the tie bar as opposed to the shear studs in the system?
That's an excellent question. The tie bars are extremely important in the non-composite phase before the concrete has been cast because they provide stiffness and stability to the empty steel module. After the concrete has been cast, they also continue to provide out-of-plane shear strength and they provide interfacial shear strength. The shear studs by themselves only provide resistance for the steel plate against buckling after the concrete has been cast and has set. So the tie bars does all the same things that the shear studs do and more, particularly in the non-composite case.
Okay, thanks. We've got more questions to get to, but first let's fit in a poll question. Let's ask the audience. I'll push out a polling question to everyone. You should see this on your screen in the moderator window. Question is this: true or false, steel reinforcing bars are always required to reinforce the concrete infill of SpeedCore walls? Is this true or false? Go ahead and click on the radio button next to the answer you think is correct and hit submit. And in a few seconds here, we'll take a look at the results. One more time, that question is true or false. Steel reinforcing bars are always required to reinforce the concrete infill of steel walls. Right. Last chance to participate. All right, Amit, let's take a look at the results. Okay, so 84% said false. Is that the answer we were looking for?
Yes.
Great job, everyone. Okay. Now let's get back to some more questions that came in from the audience. All right. The question about the coupling beams. Does the method of welding influence the performance of the coupling beam? For example, whether it's a CJP or fillet welding, that sort of thing.
The answer to that question is the performance requirement for the coupling beam to wall connection was a rotation capacity of 0.03 radians before the flexural resistance drops below 0.8 NP. And all the connections that we had selected, designed, and tested met that requirement. So whether you have CJP welds or fillet welds, as long as the connections are designed and detailed like we've talked about, they will all meet the performance requirement. When they give you better performance than that, there's not a whole lot of benefit from that in the design procedure or in the performance of the structure overall.
Thanks. Good question. Looking at the 1/2 scale model testing that was done for the tie beams between the shear walls, the question is, were the tie bars, the shear studs, the concrete fine and coarse aggregate sizes, and the steel plate thicknesses, were they appropriately scaled for that testing?
Yes, they were all appropriately scaled along with the concrete coarse aggregates and so on, and the concrete mix design as well.
Okay. Next question. This person states and then asks, the savings of SpeedCore in terms of speed of construction, carbon emissions, is a paradigm shift that can't be understated. Has there ever been any thought on the reduction of the initial embodied carbon impact? And is there future research looking into more sustainable methods to mitigate that initial impact?
That is an excellent question. This system truly provides a paradigm shift that can be brought to bear upon topics of sustainability. Because the role of the concrete in terms of its structural impact is quite limited, there is a great opportunity to look at the concrete mix designs to further reduce the initial embodied carbon. And this is some work that we are planning to do in the near future, looking at some applications of green concrete and so on in order to improve the sustainability of the system further.
We're getting close on time here. We'll try to fit in a few more questions. Next question is, are there building height limits for this SpeedCore system?
That's an excellent question. The building height limits are the same as those in ASCE 7, as long as you are using the AISC 341-22 seismic provisions. But once you exceed those building height limitations, you can very well use performance-based design in order to complete and use the SpeedCore system. For example, the Rainier Square project is 58 students in height. So it's a high-rise building application of the same.
And next question is, were there any studies performed to study the torsional behavior of the system?
That's an excellent question. So far, no studies have been conducted on the torsional stiffness or resistance of the system in particular, because they are used as elevator core wall systems in the coupled configuration with C shapes and so on. But that's something that we can definitely look at in the future. And it's probably a simple analytical study.
Okay, and then have you checked for fatigue at all, since these walls will be subjected to cycles of wind loading conditions in high-rise buildings?
Yeah, that is an excellent question. We have conducted tests subjecting these walls to almost 500 to 1,000 cycles of wind loading, simulating about a 50-year design life. And so we've looked at the fatigue performance of the walls, and the results are very good. There really are no concerns for the fatigue design. These results are forthcoming in a future publication.
And I'm going to finish up with a couple questions related to fire, and then we'll finish things up here as we push our time limit here. Question is, did you say, when you were talking about the fire scenarios, did you say that the shear studs / tie bars did not result in any kind of meaningful transfer of thermal load from one side to the other during the non-uniform loading?
That is correct. The tie bars do not act as thermal bridges, and there is no meaningful heat conduction from one side to the other. And the experimental results and the numerical models all show that.
Last question here. Thanks everyone for hanging in with us. Will or do the building codes recognize the self-inherent fire resistance
When we did the research, it was new, and for the 200 parts avenue structure in particular, the results of our research were used to justify that no fire protection was needed for the SpeedCore walls, and it was accepted by the authority having jurisdiction. The equations for the fire resistance rating and also for calculating the structural strength of the wall under fire loading have all been placed in AISC 36022, Appendix 4, and when that specification is considered and approved by the International Building Code, it will become recognized by the Building Code as well.
Very good. And actually, I'm sorry, I told a fib there. I do see we have a few questions on the same topic, so I want to ask this one as well. How are the base of SpeedCore walls developed / connected to the foundations?
There are multiple foundation to wall connection possibilities. Some of them include the simple double bar connection, the kind that is used in reinforced concrete. Some designs use steel columns or stanchions that are extended further and then embedded into the reinforced concrete foundation. And some use base plates with anchor bars in order to connect the wall to the foundation system. Multiple connections are possible.
All right, very good. Well, thank you for those responses, Dr. Varma, and thanks to all of you that submitted questions today. If your question did not get answered, we will work with Dr. Varma and the Steel Solutions Center to provide answers to those questions in the next couple of weeks. So, all right. Well, that wraps up our presentation today. And before we go, I do want to just go over how you can get your PDH certificate for today's attendance. So if you registered and are participating from your own connection, there's nothing you really need to do. We will review attendance records and issue certificates via email based on your attendance. You'll be receiving those certificates from registration at AISC.org. And it'll be about a week before those get processed, so be on the lookout for those. In addition, if you have people sitting with you today at your connection, you gathered as a group in the conference room or something similar to that, the main registrant will get an opportunity to report the attendance via an online form. And so this link will be sent out next week, and will be coming from registration at AISC.org. You'll have to log in with your AISC credentials, and once you're there, you can report everyone that was attending at your connection, and each member will receive certificates. With that, I think we'll wrap up today's session. My thanks again to Dr. Amit Varma for today's presentation, and thanks to all of you that joined us today. We hope you enjoyed it, and we certainly hope to see you join us at future webinars in the near future. Thanks, everyone, and have a great afternoon.